all the op-amps we have discussed so far have a differential input so that we can make feedback circuits with them, but have a single-ended output. What we will discuss today and in the next class will be fully differential op-amps. Now, there are various advantages of fully differential circuits. By fully differential, here I mean the input and outputs are all fully differential. So, every signal is represented by a pair of wires, and the signal will be represented as a voltage difference between the two wires. Okay. Because of lack of time, I won't discuss the advantages in detail, I'll just list them out. So, first thing is they are more immune to common interferences. That's because your signal of interest is the difference in voltage between two lines, and a variety of interferences tend to be common to both lines. For instance, you could have a wire crossing over these two, okay, in which case you will have capacitive coupling between the lines. Now, if you have a voltage change on the interfering line, then that couples equally to both lines, okay, assuming that the two lines which form the differential pair are physically symmetrical. Now, physical symmetry is another essential part for making fully differential circuits. It's not enough if the schematic is differential. Physically also they should be mirror images of each other, okay. Certainly more immune to interferences compared to a single line. For instance, if we had a single line like this, if the signal of interest was between this point and some ground. Now, the definition of ground is fairly difficult in any circuit, okay. It's supposed to be the common node, but you don't have conductors with infinite conductance. You will always have some resistance. So, there is no such thing as a single node. For instance, I draw a circuit with this thing at ground, something else at ground, and so on. The implication here is that this point and this point are at exactly the same potential. But in reality, they will be connected by some wire, which has some resistance. So, now it becomes a question of if I define some potential with respect to ground, which is it? I mean, is it with respect to this or some other point entirely? Okay. So, if you have some coupling to this point, so the ground potential doesn't change, right? So, the signal value will change, because it's whatever signal you are trying to impress on this wire plus whatever signal appears because of interference. Whereas in case of differential circuits, that ambiguity is not there. It's referred to the other wire. In fact, you can think of differential signals as transmitting both the signal wire and the reference wire for it. Like each wire is the reference for the other wire, okay. So, you don't have the difficulty with defining what the signal voltage is referred to. So, it's immune to interference. It also causes less interference, okay. So, now let us say we consider our signal as the interfering signal. It will also interfere with other signals. So, let us say we have a single-ended signal. Then if there is a voltage change on this wire, it is also impressed on the black wire, okay. Whereas now, if there is a signal between these two, that is a differential signal, what happens? Both of them couple to the black wire. So, what will be the net result? So, if this rises up and this falls down and the coupling is physically symmetrical, they tend to cancel out, okay, because this black wire is like the line of symmetry in our circuit, in a fully differential circuit, okay. So, that will be at 0 volts because of symmetry. So, signal represented like this as a signal between a pair of wires will not interfere with the other signals, okay. It is more immune to interference, but it also causes less interference, okay. So, good both ways. Now, one more advantageous aspect is that we operate in a supply limited environment, okay. So, all our swings are limited somehow by the supply. We have seen that in every case the swing limit will be VDD minus something. If the circuit is good for swing, that something will be small. So the signal swing will be close to VDD. If this is 0 volts and this is VDD, perhaps you can swing up to here. Okay. Now with a differential circuit, they are physically different nodes in the circuit. Okay. So if this node swings this way, the other node swings in the opposite direction. Okay. And the signal is represented by the difference between the two node voltages. So the effective signal swing you have is twice as much. Okay. Is this clear? If your single-ended signal can swing between, let's say, 0 and VDD in the best case, then that means you can represent a sinusoid of peak value VDD by 2. Whereas if you have a differential signal, each node can swing from 0 to VDD, you can represent a sinusoid of a peak value VDD. Okay. So you can have twice the signal swing with a differential circuit, which consequently leads to better signal to noise ratio. I have a single-ended circuit and it can swing some amount, and I have a differential version of the same circuit. How much more will the signal to noise ratio be in the differential circuit? The signal power increases by a factor of 4 because the signal amplitude increased by a factor of 2. Okay. This goes to 4 times the signal. Here I am taking it as the ratio of mean square quantities. Okay. Now the noise, we will see this afterwards. If you measure some noise here, it's a symmetrical circuit, so there will be some noise at this point and some other noise at this point. Okay, and when you take the difference, you will end up getting twice the noise mean square value. Okay. So you will get twice the signal to noise ratio. Okay. I mean, this is not for free. You will end up consuming twice the power also, but you will be able to get twice the signal to noise ratio. And also you are much more immune to interferences and other common disturbances. So one class of interferences is the fluctuation in the power supply. Okay. The interference also includes power supply fluctuations, and differential circuits have better immunity to this is again because a fluctuation in the power supply tends to be common to both halves of the differential circuit because both are operating from the same supply. Okay. And again, usually a fully differential circuit also causes less power supply fluctuations. The reason for power supply fluctuation is that the circuit draws some current. Because of that current and the impedance of the power supply line, the voltage on the power supply line changes. Okay. If we have some circuit and it's supposed to be supplied by an ideal voltage source, but it's never supplied by an ideal voltage source, this will have some impedance which includes resistive and inductive parts. Okay. The current drawn through the power supply can change with time. So which means that although this voltage is fixed, the voltage across these 2 points will have some fluctuations. Okay. Now, first of all, these fluctuations will appear in common to both halves of the circuit, assuming this is a fully differential circuit. In that case, they will not have much effect on the output, or at least have a reduced effect on the output compared to a single-ended circuit. Also, the currents drawn from the power supply in a fully differential circuit are more constant. Okay. There will be 2 halves of the circuit, and each half will be drawing currents in opposite phases. Okay. So again, the fluctuations on the power supply will also be less. So exactly like these two are general. A particular case of interference is a power supply fluctuation. Okay. So fully differential circuits cause less power supply fluctuation and also are less affected by it. these are all the motivating factors to go to fully differential circuits. Okay. What we'll do next is to go and turn our op amp into a fully differential op amp. Okay. Just before that, a sample circuit. Let's say we have, the question was, why do fully differential circuits cause lesser power supply fluctuations? Because each half of the circuit will be drawing current in opposite directions. Okay. Because the two halves of the circuit are processing opposite phase signals, right? So the currents that are drawn also tend to be of opposite phases. And both currents come from the power supply. So the variations cancel out, more or less. Now this is a very familiar single unit circuit. What is the output? Minus R2 by R1 times Vi. Now a fully differential op amp will have a differential output. Okay. Now here what did we do? We took the output signal, summed it with the input signal and fed it back to the input of the op amp. Now in case of the fully differential signal, both the input and output will be fully differential. Okay. So the input will be defined between certain 2 points and the output is defined between these 2 points. So what we do is, we sum the differential input with the differential output and feed it to the differential input of the op amp. Okay. So if I apply some Vi here, I will get minus R2 by R1 times Vi between these two terminals. Okay. So Vi is between these two, Vout is between these two. What will be the common mode voltage of the outputs? Actually, this circuit is incomplete, meaning there has to be some arrangement to take care of the common mode voltage. Another way to think about it is, here we have one output voltage and we stabilize it to a particular value using feedback, one feedback loop. Okay. Here we have two output voltages. Now we can think of it as two separate output voltages or decompose it into differential and common mode components. The differential component is stabilized by this differential feedback network. The common mode component has to be stabilized by something else. It is known as common mode feedback and it is usually treated as something internal to the op amp. Okay. Because the signals that interest us are these differential signals. Let's say it's your audio or whatever. It will be the differential input Vi. So we will make the feedback circuit for our signal and the common mode is assumed to be set within the op amp, but it needs to be set. Okay. And for that we need another feedback loop. Okay. We have two variables. To set two variables we need two feedback loops and the two variables we choose to set are the differential and common mode outputs. Okay. So any fully differential circuit that we make must have some way of setting the common mode output. Now it may not always need a feedback circuit, but frequently in high gain cases and certainly in case of op amps, you do need common mode feedback circuits. Okay. The question was, how do you decide the sign of the op amp in fully differential circuits? Exactly the same as before. How did we decide it here? How did we decide the signs of the op amp in this case? What I do essentially is I assume some signs and calculate the input voltage of the op amp as a function of the output. Now, let's say I delete the input signs. I don't know what it is. I assume some signs and calculate the input difference as a function of the output. Okay, it should be in opposite phase to the output. So that finally, let's say these are the differential output and differential input of the op amp. The characteristics are like this. You expect it to be something like this. Now the feedback network should have a characteristic with opposite slope. Okay, that's how you decide the signs. So we can go and turn all our op amps into fully differential structures. How do we go about doing it? First of all, let me draw a fully differential amplifier. This is not suitable for an op amp. Okay. These are the differential inputs, and the output is defined between these 2 points. Okay. What is the output common mode voltage? So in quiescent condition, I naught by 2 flows here and I naught by 2 flows here. So the common mode output is VDD minus I naught R by 2 okay, and on top of it you will have the differential output. Okay. So in this particular case, the output common mode voltage is fixed to some value, that is VDD minus I naught R by 2. Can we use this as an op-amp? We have discussed this before. If you load it with a resistance, you need a very large DC drop across the resistances to have a large gain. Okay. So while it's theoretically possible, it's not practical to use this as an op-amp. So what do we need to do? We need to have a very high incremental resistance here, but something that doesn't take a large DC voltage drop. Okay. And we have done this before. We use MOS current sources, MOS transistors operating in saturation region, as load devices. And again, the input is applied differentially between these two around a certain common mode, and the output is taken between these 2 points, and it has to be around a well defined common mode. Okay. So let's say this is I naught. Each of these current sources M3 and M4 should be I naught by 2, right? What will be the output common mode voltage here? M3 and M4 are biased to the gate source voltage so that they are nominally carrying a current of I naught by 2, for instance using a current mirror. So what happens if I build the circuit? Since this is the first time we see something like this, we will analyze it properly. First of all, what we are interested in is in the common mode equivalent. That is, we are interested in a condition where these 2 voltages are equal. Okay, just the quiescent condition. We have not applied any differential input. So what equivalent circuit will be used to analyze it? We will basically fold the circuit over and connect the 2 sides. If I do that, M3 and M4 get combined into a single transistor. M1 and 2 get combined into a single transistor, and the gate is at VCM. This is at whatever value is necessary. So let's say it comes from a current source. Okay. Current mirror rather. And the current mirror is designed to provide nominally a current of I naught in this. Each of M3 and M4 carries I naught by 2. So the combined transistor carries I naught, or supposed to carry I naught. And this carries I naught also. Okay. How will you determine the voltage at this node? First of all, regardless of what this is supposed to carry, finally the same current has to be going through all of them, right? That's just from Kirchhoff's law. If the upper current, if this current tends to be larger, then somehow the voltages have to be adjusted so that the same current flows through all of them. Similarly, if this current is smaller than I naught, again the same current still has to flow through it. So what will happen is, let me call this I3, okay, or I34. Let's say I34 tends to be larger than I naught. What happens then? This node voltage will tend to rise, and drain source voltage of M3, M4 will become smaller than the value required to maintain them in saturation region. Okay. Once it goes out of saturation, the current will reduce for the same gate source voltage. Okay. So, VCM out goes towards VDD. Okay. So, at this point M3 and M4 are in triode region. So, what is the problem with that? So, first of all, if your output common mode voltage is close to VDD, your swing is very small. And also the idea was to get a high gain by using a current source. Now, in triode region, the impedance is low and the gain is low. Okay. Similarly, if I3 and I34 tends to be smaller than I0, what happens is the output node voltage will tend to fall down. Okay. What happens then? Once it starts falling, okay, this transistor M12 goes into triode region. Once it goes into triode region, to conduct a certain amount of current, it needs a larger VGS. So, the source voltage also tends to fall down. Okay. Finally, this transistor and this transistor both will end up in triode region. Okay. And the output common mode voltage goes closer to ground. So, again it is a useless circuit. So, what do we do? The question was, why does the source voltage of M12 reduce if VCM reduces? As VCM out goes down, let us say this current does not change. If that happens, what does it mean? M12 is in triode region. Okay. So, what should happen to its gate source voltage? As it goes into triode region, to maintain the same current, it has to have a larger VGS, right, to compensate. So, it has a larger VGS. The gate is biased at VCM and the source will fall down. Okay. So, somehow we have to maintain I34 exactly equal to I0. How do we do that? We have to drive it with feedback. Okay. If you keep it in open loop, then it will never be equal to I0. The chances of it being exactly equal to I0 are really small. If you make a million devices like this and measure it, perhaps some of them will be sitting in the desired region of operation, but the majority will be somewhere off. Okay. So, we have to make sure by means of active feedback that the upper current source exactly equals the lower current source. How do we do this? Do we know techniques to do this? We have done this like so many times, right? Somehow sense the current and then feed it back to the gate. Feed it back to whatever controls the current source. So, let us do that. Now, I can't bias this from a current mirror. This is the common mode equivalent circuit, just to remind you. So, what do I do now? Give me one possible solution. Okay, I measure this voltage. I do this, which is plus and which is minus. Okay, what is this? So, this is the bias that I need. So, let me call it VCM out. So, this is the common mode equivalent circuit, but I want a differential amplifier. This is not just a biasing circuit, right? So, what do I do there? My real circuit is like this. I agree, if you make this to be your common mode equivalent circuit, the current through M34 will be exactly the current through M0 and the output will be stabilized to VCM out. The actual circuit I have is here. Okay. What do I do here? I mean, I need to get the same equivalent circuit, right? How will I do that? In this case, we want the differential amplifier's operation to be intact. Okay? And we want to control these current sources based on the common mode output. Okay? Of course, if we do this, the common mode will be stabilized. But then we can't use the differential amplifier, right? We still, for the differential operation, the circuit should still remain the same as before, but only for common mode, we need to have feedback around the upper current sources. Okay? Whatever we use for feedback should be sensitive only to the common mode voltage. The suggestion was to use an op-amp in the common mode feedback path instead of directly connecting the drains to the gate. So this is VCM out. What happens in this case? I mean, differentially the gain is 0. That's it, right? If the outputs are shorted, the differentially the gain is 0. Okay? So whatever feedback circuit you provide should be sensitive only to the common mode output, not to the differential output. Okay? This idea is correct. You have to somehow sense the common mode. In this case, there is only common mode because this is a common mode equivalent circuit. Okay? The question is, how do you translate to the fully differential circuit? You should do it in a way that the differential operation is not affected, but only the common mode is sensed and fed back to the current sources. Okay? So he says, why not use 2 op-amps? It's rather extravagant, but that's okay. Where will I connect this to? Okay. So I'll just connect it like this. And what will be the differential gain in this case? The output voltage is, see, if this is VCM out and this is also VCM out, each of these voltages individually is VCM out. Okay. Let's take this part of the circuit. This is what we have. What is the impedance looking in here? RDS. Why? What happens if I wiggle this node by some amount? So if you have V here, what will be the voltage here? A times V. It's A times V at the output. So what is the current drawn here? A times GM times V. So the impedance is 1 over AGM. So if you use a very good op-amp, the impedance is 0. Okay. So that's what has happened here. You have substituted the load resistances with 0 resistance. So that's why the gain is 0. Okay. Not only the differential gain, but each of the voltages individually doesn't fluctuate. Okay. Another suggestion is to not use an amplifier, but use a direct connection. 1 over GM. Yeah, so that's also not good, right? You need a very large RL of the order of RDS, the order of 1 over GDS. Now we have got of the order of 1 over GM. Okay. First of all, we shouldn't break the connection between the two gates here. Okay. We want the circuit to operate symmetrically. So I would think that you would need same current source here and there. Okay. And what was our objective? Why did we go through all of this? The common mode voltage was not fixed. Differentially there was no problem. I mean, if the common mode voltage is fixed, if all transistors are operating in the desired regions, then differentially the circuit will give you high gain and you can use it as an op-amp. The idea was to fix the common mode voltage. So what do? First we detect the common mode voltage. This is V1, V2. We need some circuits that gives us effectively V1 plus V2 by 2. Okay, then what do we do? So now we can use our feedback technique. Okay. In steady state, V1 plus V2 by 2 will be VCM out. Okay. And what will be the differential picture? It should be the same as before. That depends on the common mode detect circuit a little bit. But let's see. Is this clear? We detect the common mode, compare it to some desired output common mode voltage, and then control the upper current sources based on that voltage. Okay. First of all, what's a common mode detector? How will we find V1 plus V2 by 2 from V1 and V2? Put two resistors, then that's probably the simplest thing, right? You put two identical resistors. So this does work as a common mode detector, right? What effect does it have on the differential picture? When I draw the differential equivalent circuit, I'll have this point to be at 0 volts. So I'll have RCM loading the output. Okay. So the total conductance at the output will be RDS of M1 in parallel with RDS of M3 in parallel with RCM. So the gain will reduce, and we can increase the value of RCM as much as we can and try to minimize this effect. Okay. Resistive common mode detector works very well, but the only disadvantage is that it also loads the output. Let's see how to take care of that afterwards. Okay. Now, what is a simple thing that we can use for this op-amp? Direct connection. So I want a positive gain from this point to this point. Okay, I'll settle for a gain of 1. Just like I did for the diode-connected transistor, right? I want it sense at the drain and feed it back to the gate. Then I settle for just connecting the drain to the gate. Here I'll do the same. We have seen the circuit before in quiz 2. So it was with NMOS, but it's the same circuit. So normally it is drawn. Okay. So what is the output common mode voltage now? If you bias the inputs at VCM, you can just use symmetry arguments to argue that both V1 and V2 will be at the same voltage. Okay, and that will be equal to VCM out, and the midpoint will also be at that voltage. So the common mode equivalent circuit will be now, as far as DC is concerned, the resistance has no effect at all because no gate current is flowing. Okay. So this voltage will simply be VDD minus VGS of M34, which is the same as VGS of M3 or M4. It's VGS of M34 at a current I0, or VGS of M3 at a current of I0 by 2. Okay. So you can't set it completely independently, right? You can't say I want 1 volt here. right? It will depend on the sizes of M3 and M4, which may be sized for other constraints. I mean, you want M3 and M4's GM to be something for noise and GDS to be something for gain and so on. Okay. So the setting of the output common mode is not completely independent. It depends on the quiescent VGS of M3 and M4. But this circuit works. You can use this under some circumstances. Okay. This is the common mode equivalent circuit. And also, analyzing fully differential circuits is easier than analyzing the differential to single-ended op-amp. Okay, because now the circuit is fully symmetrical. This will be at 0 volts for differential excitation. This will be at 0 volts for differential excitation. So what do I do? How will I simplify the analysis? Analyze only the half circuit. Okay. This is grounded. So that's all that's there to the circuit. What's the gain of the circuit? What's the voltage here? What is the incremental voltage there? Minus G1 by GDS1 plus GDS3 plus the common mode conductance times VD by 2. Okay. That is V1. Now if I call this V1 and this side is V2 under differential excitation, I will define my output to be between these 2 points. Okay, that is V2 minus V1. And V2 itself is minus V1 because of symmetry under fully differential excitation. This question was, there is feedback around this circuit. Okay. Do we still need common mode feedback under these conditions? What is the answer? What happens if there is no common mode feedback? So let's say the input common mode voltage is 0. Okay. So what this network is doing is, I define this to be the output and this is the differential input VD. Okay. Or let me define it the other way perhaps. So this network is giving me VD to be equal to if I have a differential input Vi, okay, where does the common mode come into picture? Let's say this is at a certain common mode voltage. Okay, this is at a certain common mode voltage, and now I will consider 0 differential input. So that is, these two are tied to some fixed voltage, and I will assume 0. It can be anything. Okay, let's say this is at VCM out, this is at VCM in. Now, what will be the current through these resistors? VCM out minus VCM in by R1 plus R2. That tends to flow through each of the resistors. Okay, that still doesn't say that the output common mode is stabilized. Okay, the output voltage will change. Like she pointed out, the current will flow out of the transistor. So the output common mode will change, but it may not change to the correct value that you want. Okay, the output common mode voltage will change because the output impedance of the op-amp is not 0. Okay, the op-amp has a certain output impedance, so when you draw current from it, the output will change, but it doesn't necessarily change to the right value. Differentially, the circuit works regardless of the value of R1 and R2, meaning it depends only on the ratio. I can use mega ohms here or kilo ohms. Let's say I use a very large value of resistance. Okay, in that case, the common mode current is negligible, but differentially it still gives you this gain. Okay, so we do need a common mode feedback circuit. Another way to think about it is we have two variables, the two outputs. So we somehow need to stabilize both of them. Okay. Is this clear? The question was on the need for the common mode feedback circuit. When you already have a feedback around the op-amp, you always use op-amp in feedback. But in this case, that feedback for signal refers to the differential feedback. You represent the signals as differential signals, and differentially you have feedback around the op-amp. But the output common mode voltage of the op-amp still has to be set. Okay, and typically that's considered to be the internal business of the op-amp, because the user is interested in the signal processing chain. Okay, how the signal propagates through the chain. So you want to make a differential amplifier, that's why you go and do this. You're not interested in also stabilizing the common mode loop so that the op-amp functions. Okay, so when you make a differential op-amp, you need to provide the common mode feedback internally, so that externally you can think of applying differential feedback and using it in whatever application you want. Okay. Question was that should you choose the input and output common mode to be the same value? Now generally that's a good idea, because otherwise you will have common mode currents flowing here. Okay, nothing wrong with it. In some cases you may do this also, but generally it's a good idea to choose in continuous time circuits to choose the input and output common mode voltages to be the same. So this was the differential equivalent circuit, and the output is V2 minus V1, which is minus 2V1, right? So the gain of the circuit is this much. So we'll continue this tomorrow.